Periodicity. Today we're going to talk about the different trends that we observe in the periodic table and how we can use those trends to make some assessments to the various properties, chemical and physical, of the elements. Let's, let's start with the atomic radius itself. If you look at the periodic table, you will notice that going from top to bottom on most any group tends to increase the atomic radius itself. So you can see here the values. These are not the molecular masses. These are all atomic radii in angstroms. Um, the values increase as you go from top to bottom. So from hydrogen to lithium, we go from 0.53 to 1.52. From lithium to sodium, we increase it to 1.92. Going to potassium, we're now up to 2.27. Rubidium 2.48, cesium 2.65, and francium 2.70. So needless to say, the atomic radius increases as we go down a group. And the main reason that happens is because as we go down a group, we're increasing the row number. And if you recall from our previous lecture, increasing the row number tends to increase the energy level where the electron is located. And at higher energy levels, the radii of electron to nucleus tends to increase. So by that logic alone, you could say, yeah, going from a lower energy level to a higher energy level will increase the size of the atom itself. So the trend of top to bottom in terms of atomic radii makes sense. All right, so basically, as I was saying, yes, the size of the elements increases as you go from top to bottom, right? And it's all due to the fact that we have higher energy levels, the 1s, the 2s, the 3s, the 4s, the 5s, the 6s, being the corresponding valence electrons or valence orbitals of all the different alkali metals and hydrogen included in the group. Now, when you scan the elements from left to right, you see also a trend, but the trend is a little bit more mysterious as to why it happens. And we're going to analyze the reasons as to why this is happening in the first place. But starting with the second row, if we look at lithium and we move on to beryllium, we see that the size decreases. It goes from 1.52 to 1.11. And when we go from beryllium to boron, the size decreases further to 0.83. Then it goes down to 0.77 when we reach carbon, down to 0.70 when we reach nitrogen, down to 0.66 when we reach oxygen, down to well, it should have gone down by the time we got to fluorine. There's a reason for why the value for fluorine is not decreasing. We'll probably touch upon that a little later. And helium actually goes up, way up. There's also a reason for why that value is not going down. But up until oxygen, you see that there is a trend which kind of depicts a decrease in the atomic radius. Now, the interesting thing is that you are actually adding more electrons and more electrons and more electrons. So it's a little counterintuitive that as you increase atomic number going from left to right, that you would have a smaller radius altogether. But the reason this is happening is because of something known as the effective nuclear charge. The atomic radius of the element decreases whenever the effective nuclear charge goes up. And you may be asking yourself, well, what the heck is the effective nuclear charge? And I am very glad you asked, because I'm about to tell you. Okay, the effective nuclear charge, which in this lecture and from here thereafter I'm going to be expressing as Z subscript EFF. Basically, what the effective nuclear charge is the idea that when you have an electron, on the outside energy levels, like valence electrons, for instance, you do have some core electrons also closer to the nucleus. And if you look at it this way, the red electron, which is one of the valence electrons, has to basically kind of maneuver its charge towards the nucleus by basically kind of fighting the other electrons. And in a way, the core electrons are basically shielding part of the positive charge of the nucleus away from this electron. So this electron only sees a portion of the nuclear charge itself. And because of that, we call it the effective nuclear charge, just the amount of charge that the electron happens to see. If you look at your textbooks, they'll even give you the following formula, that the effective nuclear charge is equal to the atomic number, aka the number of protons, or the total positive charge in the nucleus minus the shielding experienced by the core electrons. And usually that's where books leave it. They say, yeah, so there is effective nuclear charge, and it affects how the electrons are bound to the atom and what they do. I personally think that that is not a sufficient explanation of the effective nuclear charge, and we're actually going to dwell deeper into this topic. But I need you to definitely know the symbols, right? So ZeF is the effective nuclear charge. Z itself is just the atomic number of the element. S is the shielding constant. And what we're going to do is calculate the effective nuclear charge by first calculating the shielding constant. And in order to do this, I'm going to present to you a specific um, set of rules known as Slater's rules to approximate the shielding constant in a relatively simplistic manner. There's two requirements to use Slater's rules. The first one is that you have a periodic table handy, and two, that you are comfortable writing electron configurations. Electron configurations are going to be very important for using Slater's rules and determining the effective nuclear charge, which itself we will use to approximate many other values. Alright, so I'm going to walk you through what Slater's rules is. The first thing you do is you write the electron configuration of the atom in question. So let's say the atom is carbon. The configuration will be 1s2, 2s2, 2p2. And then what you do is you rearrange the configuration such that this increases in order of n, and within orders of n, you increase this in values of L. So that's to say that, let's say for the third energy level, you would have s orbitals, p orbitals, d orbitals, f orbitals. Exactly in that order is how you want to arrange them, but you want to have all the energy 3 orbitals together, followed by all the energy 4 orbitals together, etc., etc. Now in this case, if we look carefully, we see that, okay, well, we have the first energy orbital at the very beginning, followed by the energy 2 orbitals. And this is going from S to P, which is the correct order for L. So this is actually done. For this particular element, we don't have to do anything extra. In future examples, I'll show you exactly what the second rule ultimately means. The third portion is to take S and P orbitals of the same energy level, and basically you're gonna group them together. The D's and F's are left alone, whatever state they're in, but the S and P's of the same energy level are grouped. So that's to say that here we have a 2s orbital with 2 electrons and a 2p orbital with 2 electrons. We group them together and we say that entire group has 4 electrons, right? It's basically the sum of those two. All right, now to determine the shielding, what we need to do is apply the actual rules given by Slater. And the rules say the following. In regards to the group of electrons that you're trying to calculate the shielding constant for, if you have electrons that are even in higher groups, meaning groups farther to the right, those will not be contributing any shielding whatsoever because they're not closer to the nucleus than the electrons that you are examining. However, electrons that are present in the same group, aside from the one that you're calculating the shielding constant for, do shield to some degree the one electron you're doing the calculation for. And the one that we're going to be mostly playing with is the 0.35. The 0.30 only applies to hydrogen or helium, but the 0.35 is the one we're going to be using the most. And what this says is that if you have X number of electrons in the same group, aside from the one you're calculating the value for, each one of those extra electrons will be multiplied by 0.35. And that's only if the electrons that you're calculating the values for are S and P, right? And then here we have another column that means that the electrons that we're calculating the shielding for are D or F electrons. Now, groups that are one energy level below the one that you are calculating the shielding for, however many electrons you have, get multiplied by 0.85, as long as the electron that you are calculating the shielding constant for is an S or P electron. If the electron you're calculating the constant for is a D or F electron, any group of lower energy value is going to shield by a whole charge. And thereafter, if you have groups of lower energy values still present to the left, they're going to shield completely. Okay, so this is what Slater's table needs to be applied to this problem right here. And I'm going to kind of finish the problem so you guys see. I'm going to, first of all, make the graph a little bit more, amenable, a little bit more simplistic and smaller in size. But we're going to start with, I'm going to calculate the shielding for the 1s electron. Now the shielding for the 1s, as the table says, you have to use 0.30 for the shielding. And here we have two electrons. Only one of the two electrons is going to be shielding the first one. So technically speaking, the only shielding you have here for the 1s electron is just 0.30. But if you try to calculate the shielding constant for the 2s2p electrons, you have 4 electrons total. So 3 out of the 4 will be shielding the fourth one. So notice here that I am multiplying the 0.35, and we're using 0.35 because these orbitals are not the 1s. We're multiplying the 0.35 by 3. And when you carry the math, oh yeah, of course, the 2s2p have a group that's further to the left, which is the 2 electrons in the 1s orbital. So those 2 electrons get multiplied by 0.85. That's the group that is 1 less than the energy level you're examining. When you add all these values together, you get 1.05 plus 1.7, which ultimately is 2.75. And to determine the effective nuclear charge, all you have to do is subtract these numbers from the atomic number of the element. And for carbon, the atomic number is 6. So you'll subtract the 0.3 from 6 to get the effective nuclear charge of the 1s orbital. And you subtract the 2.75 from 6 to get the effective nuclear charge of the 2s2p groups. And what you find out is that you have a value of 5.70 for the effective nuclear charge of the 1s orbital and a value of 3.25 for the effective nuclear charge of the 2s2p. And the idea is that the higher the value of the effective nuclear charge, the closer to the nucleus you are. So the 1s orbital is indeed closer to the nucleus because it has a higher value than the 2s2p group. Okay. We're going to continue this discussion in the next video, but for now, let's stop at this point.